Hello, welcome to this video on integration by parts. I probably should get rid of that for future reference, and because as this evolves into different textbooks, it will undoubtedly have a different section number. So let's take a look at what integration by parts is all about. Now, integration by parts is a way to integrate functions that are multiplied together. Essentially, you're sort of undoing the product rule under certain conditions. So you see, like, here's just some random examples, like x cubed times ln of x dx. Actually, ln of x dx is integration by parts. You might be thinking 1 over x, but you'd be thinking backwards. In other words, the antiderivative of 1 over x equals ln of x. But the antiderivative of ln of x needs to be derived by integration by parts. So you can sort of think of this one as, even though it has two things multiplied together, dx can be considered one of those two things that are multiplied. So it's not, you might not always see, like this one with x arctan of x. Arctan of x by itself, without the x, would be treated as integration by parts because you would treat dx as part of the multiplication process. So, okay, here's a little, you can go through this. I would never ask this, how to derive this on the test, but it's showing the product rule, then you're integrating the product rule, yada, 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 and you end up with this formula right here. This is the important part right here. The integral of u dv equals uv minus the integral of v du. One of the most important part of this process is choosing what u and dv are going to be between the two things that are multiplied together. Now, we're going to start with a particular grouping of problems that sort of all fall under the same approach. These all fall together. Then we'll look at the, like the natural log and the arctans and arc functions have their own approach, but they're all under the family of integration by parts. Now, this is if you have x and n has to be a positive integer. So you could not integrate like the square root of x times e to the 2x. I mean, one thing you have to realize, in mathematics is not every function can be integrated. Now, any question that you are asked on an exam can be integrated. There's not a process where, none of the above because you can't integrate it. But in theory, you can't automatically integrate every function. Like, for example, I'll show you, put in, bring up Maple here, and I'll just do this real quick. Square root of x times e to the x. And that's not good. Capitalize and sort of earth. If it earthed on us, that's not a good sign. Well, that means it just can't be done. Earth stands for some sort of error function or something. But anyway, all right. Point made is, yeah. So, but obviously you're only going to be asked functions that can be integrated. Now, one thing to keep in mind based on other integration techniques is, obviously this does not supersede regular substitution when it would apply. You wouldn't be asked a problem to solve by parts, but where substitution applies. But if you had just some random problem thrown at you like this example, x squared times e to the x cubed, and it just said, hey, integrate this. Might look like integration by parts, but it is not, because you can just use straight up substitution. It turns out being real easy here. So, but obviously, if I instruct you to integrate it by parts, then it would not be substitution. But that's just part of the skills of integration, is the more you learn, the more you try to look at and recognize what it would fall under. And, that's why they invented erasers and things like that. So you can, if you mess up, you can start over. And here's sort of Stewie here. He's letting us know to make sure we solve by substitution. But like I said, if it says integration by parts, it will be integration by parts. Now these three rules right here are kind of good to know. It'd be a good idea to commit them to memory. It'll make process faster for you when you're doing integration by parts like this. But you can formally derive each one of these by substitution real easily. So like e to the ax will always be 1 over a e to the ax plus c, and that comes from substitution, because if you let u equals ax, du equals a dx, I didn't write the next step, but that would be 1 over a du equals dx, and that's where the 1 over a is coming from in all these. But this would just save you a lot of time. In other words, if you had, now you see the only difference here is there's a negative. That's because the antiderivative of sine is negative cosine, antiderivative. But these would just be quick to be able to write them down, because it would kind of say, and you'll see why here coming up in some of these other problems, why that could be a little time saver there. So instead of working it out, for example, if you look at something and part of your integration by parts process is going to involve integrating, like say, cosine of 5x dx, it would just make things easier for you if you immediately knew that that was 1/5 sine of 5x. Anything to save a little time. This is the part of the calculus course here, this section plus the next three, where you can have quite some lengthy integration problems. So anything that saves you a little time and effort for a problem is very helpful. This is kind of reaching the meat of the course, so to speak, or some people call it the pinnacle of calculus, actually. This advanced integration. Anyway, now this x, we're integrating x times sine of 3x dx. Now what I'm doing here is I'm purposely doing this wrong the first time just to show you. And I won't do that anymore, but I want to show you this. Now the one thing to keep in mind when you choose the u and dv, so whatever dv is, at a minimum dv is going to have dx with it. There are problems where dv could just be dx only, but dv includes dx because it is a derivative. dv means it's the derivative of v. So it's like one part's a derivative, one part's not a derivative. So I said, let's let dv equals x dx, and then u is sine of 3x. So before you go one step further, even though I've told you this is wrong on purpose, I drew these arrows strictly to show you that before you take the next step, is that u times dv has to match what you are integrating here. Then it's definitely wrong if that's not the case. This is wrong for a different reason, but not for that. But you see, look where I have those two arrows there. You multiply those together, yeah, it'll be x sine of 3x dx. So we're okay there. That's not what the mistake is. But yeah, you might as well check that or don't go any further. Now this is very important because we're trying to piece all this together to get everything back into this formula right here. So if we have dv, we're going to need v. v is just the antiderivative of dv, and then du will be the derivative of u. So if u is sine of 3x, do not forget the chain rule. That's so easy for people to forget. The sine of 3x, if I ask people that, in a face-to-face class, they'll go cos of 3x, assuming they're not looking at this on the screen. But a chain rule, you got to take the derivative of 3x, which will be 3. So it's 3 cos 3x. And now this is dv, so the antiderivative of x would be 1/2 x squared. So now, here's the formula. So the first part of this is multiplying u times v. So we have 1/2 x squared sine of 3x. And we don't really care what that turns out to be as far as how complicated it is, because notice that part, the uv, is not requiring integration. It's the v du. So the whole idea of this process is that the v du needs to be a sort of a reduced integral or simpler integral to work with than what we started with. And let's see what happens. So here's the v, 1/2 x squared. Here's the du. You multiply these together, 3/2 x squared cos of 3x. So instead of, this x going away, which would have been helpful if that would have gone away, it now got worse. It got to be a higher power. So we've created a more difficult situation than we started with. So back to the drawing board. This is where we can pull out our eraser. So let's say, what if we reverse this now? What if we let u equal x and let dv equal sine of 3x dx, like I've done right here. I just kind of drew that arrow again to show you that u times dv must equal what you're integrating, and it does. So let's see if I put, yeah, okay. I didn't do that just yet. I guess I'll do that after this. Well, let me finish this problem. I thought I had this defined right here. I know I have something coming up later in the notes that talks about this, but, oh yeah, well here it is, okay. Yeah, sorry I skipped over this, but now I came back to it. When in this form, u equals the x and dv equals either one of these three, whichever the other part is. So that, by letting u be sine of 3x, I was automatically wrong, but I wanted to show you that it was wrong, and we did. So the u has to be the x to the power. Okay, so that's why that was wrong, and it turned out being wrong. So you can't just use these interchangeably. That's what I'm getting at, to get and still get it to work. So this is the correct way to do it. So if u is x, we have du is dx. If dv is sine of 3x, now remember we're integrating this time, so it's not 3 here, it's 1/3 when you're integrating. So the antiderivative sine of 3x would be negative 1/3 cos of 3x. Remember these little things I explained to you right there? That's why those are good to know without having to put too much work into it. So now we use the formula again. uv would be negative 1/3 x cos of 3x minus vdu, which is negative 1/3 cos of 3x dx. Now, since they're two negatives, I just made them positive. The 1/3, obviously, you can pull outside the integral if you want to. But now, see, the x has gone away, so we're just integrating cos of 3x. So this generates then a 1/3 sine of 3x, in addition to the 1/3 we had right there. So in the last step, all I have to do is multiply the two 1/3s together, and then to get 1/9, tack on a c, and there we go. And let's see what Maple says. Yep, Maple likes what I have. They're just reverse order, but that's it. So that's a very nice elementary integration by parts problem. Let's try x e to the 4x. The u needs to be the x. So that means the dv will be e to the 4x dx. So the antiderivative of e to the 4x will be 1/4 e to the 4x. Once again, to go from dv to v, it's an antiderivative. And then the derivative of x would just be dx. So we're going to piece it together using the formula right here for the integration by parts. And I just kind of drew the arrow again to show that those two things multiplied together do equal my original integral. So here we have 1/4 x e to the 4x minus 1/4 just e to the 4x dx. So the 1/4 can come out or stay there, because now the only thing you have to do is take the antiderivative of just e to the 4x, which we've already done right there. So we just use that again, and that gives me another 1/4 e to the 4x. So the 1/16 comes from this 1/4 that's here, plus another 1/4 that I say plus, times another 1/4 to make 1/16. And then we have the first part, which we didn't have to integrate that, so we didn't care. And then plus c, and there we go. Now, on these problems, now we've only used x, but what if x is raised to a higher power? Like x squared, x cubed. Technically, that means you have to repeat integration by parts. In other words, you have to perform integration by parts as many times as what that exponent is, which I'm going to show you how to do that manually, but then there's going to be another little technique I'm going to show you That's a real big time saver here. So, like, let me jump over to Maple and show you. Like, say if we had fix this up. I want to make this x to the 10th. That would actually manually would require 10 integration by parts. And there we go. Now the answer just factored out an e to the x from everything here, or whatever. Yeah, that doesn't look like fun. It really isn't. It's just, that would be very tedious. Not that it's too complicated, but keeping track of all the numbers would be the hard part of that. But we don't ever want to have one with x to the 10th, so I wouldn't worry about that. Here's an x squared. So I want to repeat the integration by parts twice. I'm going to show you another method. So here's, so the u has to be the x squared. dv will have to be cosine. Just drawing my little arrow there, showing, there. Go, hey, look at this. Multiply together. How about that? They equal what I integrated. Obviously you don't have to use that, arrow when you do it. But, boy, I sure would just take a quick look there to make sure that this is the same as this, or you're completely wasting your time. The derivative of x squared, of course, is 2x. The antiderivative cosine is sine. So using the parts formula, we have uv, which is x squared sine x, and then minus the v du, which will be 2x sine of x, because there's the du right here, and v du. Oh, I'm sorry. Okay. Yeah, that comes from up here. I jumped ahead of myself here. Sorry. So we have right here, v du is this part right there, 2x. I was looking at the wrong row here. Sorry about that. Maybe I don't know if I should drop that down. I've always wondered about that, so I think I will do that. We'll see what that looks like. Might change the notes to reflect that. Well, anyway, if you look at what's left there, maybe I didn't do it because of this reason. Creates a little bit of a crowd there. Right. Smash it in, not too bad. Anyway, let's go back up to that bottom line there on the top page. Right here. So that comes from here. But see, the issue is we still have an x times the sine of x. So that means this integral that's left also requires integration by parts. So it has to be done twice. Now you got to be careful because you're following that negative. You could pull the 2 to the outside, but then you would have to remember to distribute it back at the end. If that's okay with you, do it. I didn't. I just chose to, even though I said the u had to be x, which is correct, I didn't clarify that it could still be some number times x. So in this case, I just left the 2 with the u and then didn't pull it outside. That way I don't have to multiply it out back at the end. But you do whatever makes you happy here. So I didn't clarify that in the rules earlier, but there's no problem with a constant being there. So 2x will be 2 dx. Antiderivative sine of x is negative cos x. Now you got to be careful because it's following a negative. So uv right here will be negative 2x cos x. Maybe this was a better place to put this. And then v du, negative 2 cos of x. So remember, that's the minus from the integration by. That's the minus from the first one. Here's the minus from the next one. There's a minus from here. When you have v du is negative 2 cos x. Oh, well, look at that. Can't believe it. Somebody that called me out on this before. There should have been an x there. Yeah, trig functions don't mean anything without the variable there. Now I'm not using a stylus, so let's see if I can make this look reasonable, sort of just using the mouse. I knew something looked weird there. All right. Close enough. So we have, there we go. So now anyway, so I use this minus. Oh, then the parentheses needs to be there too. So we have, so that minus minus makes plus, but keep in mind we had this minus on the outside. So you should put those two, oh, and the antiderivative of 2 cos x would be 2 sine x, positive. So now we just have this negative in front, so you have to send that through the parentheses, and you have, that makes that plus 2x cos x, and then minus 2 sine x dx. And Maple agrees with that. Notice in that Maple software, which is, they don't bother to put the plus C there. I guess they just assume that that's understood. So I don't know what. Seemed like that wouldn't have been that difficult to program, but had nothing to do with it. So now this technique that the Larson book uses is called a tabular method for parts. You know, as we change textbooks, I think I would probably still teach this method to students, even though it's not in the book. I've had students, yeah, because this is not really a form that's not in every book, and not everybody would be aware of this. I had a student years ago that we learned this, and she came back to me and told me she had differential equations class, and then she did it correctly on a problem on a test. The instructor wrote, "I don't know what you did here, but this worked." So the instructor doesn't necessarily don't know tabular method if they haven't seen it, but that's because the professor would have just used repeated integration by parts. So that's what they wouldn't have seen this, and she explained what the method was called. He must have looked it up or whatever and said, "Okay, that's fine." But it's pretty slick method. I like it. It's very, especially if you get anything higher than square, you know, x squared. This works beautifully. But the point is, if not, if you forget this method or something goes wrong, you can always do manual integration by parts. I don't think on a test I would ask, I don't know, I'll say 3 times parts maybe, but if you're doing the tabular method, it won't be that difficult. 4 at the most. I don't like to go too crazy on this. Okay, so what you do here is you set up a column here of U and dV, and what I did, I just took any of the possible scenarios here for now, E, sine, and cosine. Okay, and on the U is always going to be x to some power, or, you know, like I said earlier, you could have a coefficient in front of it if you wanted to. That's not going to hurt anything. So what you do on the U side is you differentiate down until you reach a constant. Don't go all the way to 0. Go till you have a number that's not 0. First non-zero constant. Because obviously the next derivative after the constant would be 0. Now here you got to be careful, and this is where people mess this up. This is a dV column, means we're integrating as we go down. Yeah, that's the biggest mistake I'll see people make is on a test or something, is they will, on an exam, they'll, like if let's say if there's e to the 3x, they'll put 3e to the 3x, 9e to the 3x, so forth, so on. They were actually differentiating instead of integrating. And so that it would go e to the 3x, 1/3 e to the 3x, 1/9 e to the 3x. So we're integrating going downward. Now what you have to do is you have to go one more. You start across here, and the dV column has to go one more step than the U does. You have to go one more line here below the constant, because what you're going to do, and let me talk about this. And you have this sign chart. It starts at plus, goes minus, plus, minus, plus. It would keep alternating. Like I said, I'm not going to get too crazy on this, obviously, but it would keep going, plus, minus, that same pattern. But to link your answer together, what you do is you multiply this one right here times the one immediately below it to the right. That would be part of your answer. Take the next one below it. Next one below it, multiply, and you incorporate this sign with it. Now the ones that have the plus aren't going to affect anything, but the negative absolutely will. it'll change whatever the sign of those two numbers are multiplied together. So it's really the negative that's the important one here. But once you see this is done, it's real super easy and convenient. Like this one, x cubed cosine of 2x, if you did it manually, it would take integration by parts 3 times, which, is doable. But, integration by parts has that negative in the formula, so you have to keep track of, negative with a new set of parentheses with another negative in there. And, boy, getting all the signs right could be difficult. Well, here we go. I start with x cubed as my u. And look at my sign chart here. Plus, minus, plus, minus, plus, minus. Because I stop. I'll just make it green for the heck of it here. And then you go x cubed, 3x squared, 6x, 6. Stop at 6. That'll be your last derivative. So that means I know I go one more than that on the right side. So you just take the antiderivative of cos of 2x. Now it's going to keep putting a multiple, just like for e it would. You'll just keep putting a multiple of 1/2 out in front of it. But obviously going from cosine to sine is tricky because you got to remember the plus or minus. But you're always going to go, cos will go 1/2, then 1/4, 1/8, 1/16. But the antiderivative of cos is positive sine. The antiderivative of sine is negative cosine. Now the antiderivative of cosine is just sine, but you already had a negative here, so the negative stays there. And then the antiderivative of negative sine would go back to positive cosine. So what you do is you link those together, and so you multiply these two together. That gives you 1/2 x cubed sine of 2x. And then you multiply these two together, but you use this negative out here. So this negative times that negative makes it positive. You have 3/4 x squared cos of 2x. The next one is that plus, so it doesn't affect anything, but you got a negative here. Yeah, I went ahead and reduced it here at the same time. I'm sure when you're picking an answer choice, it's going to be reduced, but that's not difficult, obviously. So it's negative 3/4 x sine of 2x. And then use the negative right here. Those are positive, but that makes it negative. So it's negative 3/8 cos of 2x plus c. And that matches the maple. Not in the terms are not in the same order, but it matches. That's pretty slick. I like that. So feel free to use that for these kind of problems. Now there's the next type of integration by parts problems. We won't need this method, but for the x with e, x with sine, x with cosine, I would strongly suggest using it. Especially this one, you would have to integrate by parts 4 times. That kind of looks like that e to the 10th one, or that x to the 10th one I showed you in Maple there, how they factored everything out. Well, let's take a look at this one. So you let u be x to the 4th. You differentiate this down. That's easy enough. So you get to 24. And then we have to integrate e to the negative 2x. Now the e is a little bit easier than sine and cosine because you're not keeping track of the antiderivatives themselves being plus or minus. All you're doing every time is multiplying by 1 over that coefficient. So negative 1/2 times negative 1/2 makes 1/4. Times negative 1/2 is negative 1/8. Times negative 1/2 is 1/16. Times negative 1/2 is negative 1 over 32. All right, there's our plus, minus, plus, minus, plus. I got the lines connecting each other there. And connect the terms. And that'll be the answer. All right. So you connect these. And remember, the minus is the one that's going to affect it. There, it's going to affect the signs. Well, this one's kind of unique because they all turn out to be negative. Because this is plus times minus, and that minus from the formula comes out to be plus plus minus. Plus minus makes minus. Minus times plus is minus. Plus times minus is minus. All of them are negative. See, they factored out a negative right here. That way it leaves everything positive there. And pretty easy. Just connect them like that, and it's a big, long, ugly answer. But using this technique makes it a much, much more pleasant way to get that answer. All right. We have, now let's look at combining x with ln. Now this time n can be any real number, so we could actually integrate for this one, for ln. But here n has to be a whole number. And the difference between saying whole number and positive integer, like I said earlier, which saying it's a positive integer is the same thing as saying it's a natural number, a counting number, 1, 2, 3, 4. That's the same thing. Whole number means that you could have x to the 0, meaning that would be 1, so that would be, meaning you can integrate arc by itself. That's all that's saying. So you could have 0, 1, 2, 3, 4, 5. You can't have negatives here. Come over here. X raised to the negative 2. And I'll just put, I don't know, arc tan of x. Oh, actually that is doable then. There must be a different technique here or something. Well, anyway, I'm going to abide by my rules here. Looks like that one was doable. But this one I know it should be doable. I just want to show you, like the square root of x. Well, I will absolutely not ask that on a test. This one, I'll make sure they're all positive exponents. But that kind of has me curious. I'd be interested to see. Oh, I think I see the technique that would be required here. But anyway, that's okay. Let's not worry about that. Yeah, now that's doable. So that, that square root of x we saw earlier when what I put it with, I think I put it with e or whatever, and it freaked out and kind of earthed and all that kind of stuff on us there. But this is perfectly fine. So x can be any real number. Okay, let's go back here. Now for these, the dv is the x, or just dx if there's no x there, just dx. So this is different. So with all the other ones we've been doing, the u is the x. Not true here. The u has to be ln if ln's involved. It's arc something if arc is involved. I don't know why I don't have arc something there. Did I accidentally erase something there? No? Might have drugged my eraser over something there. Anyway, x should be arc. Alright. Okay, well, that's alright. Alrighty. Yeah, and here's what I was telling you earlier. X, ln of x, ln of x dx by itself is using parts. So you see I let the u be ln of x, dv is dx. That way the derivative then of ln of x will be 1 over x. The antiderivative of dx would just be x. So we have, okay, the parts, there's the parts formula. So we still follow that. So uv will be x ln of x right there, minus vdu, multiply those two. So you multiply those two together, right there, you see right here, you just get 1 dx. So the antiderivative of dx would just be x. So you have x ln of x minus x plus c. That's the antiderivative of ln of x. Now here's one with the x on the bottom. No problem. You just bring it up and make it x to the negative 2. And you let u be ln of 2x. And then you let dv equals x to the negative 2. And I'm just kind of drawing my little arrows there just to show you that u and dv multiplied together equal exactly what we're trying to integrate. Obviously, that's important. Now, I wrote this right here, kind of review back to natural logs. It's very common for students, and I can see why you would think this way because this looks like it would be right. So if I just quickly ask somebody, what's the derivative of ln of 2x? A lot of people would say 2 over x, but it is not. If the 2 is in front of ln, it would be. But think of it this way. If you actually take the derivative of it, it's the derivative of 2x over 2x. So the derivative of 2x is 2, right there, over 2x, so it's 1 over x. So the derivative of ln of some coefficient of x, is always just 1 over x. Okay. So now we piece it together according to the parts formula. Now, this could be a little confusing here, but I tried to make it a little. So what I did was, to make it easier for integration purposes, this du right here, I just rewrote it as x to the minus 1, because that way it makes it a little easier to combine them together. So here's your uv right there. We don't care what that looks like. We're not integrating it. We just care that it's accurate. But we're not worried about the complexity of it, only what we have left here. And so you have these two multiplied together, which will be x to the negative 2, and then you just do the basic power rule for that. You'll get minus x to the minus 1. Negative exponents are fine. You know, on multiple choice question, you may have to drop them, pick the answer where they're dropped back down, like right here, choosing the answer. When someone's taking a face-to-face class with me, I'm always flexible about I have no problem with an answer having negative exponents in it. That's terrific. Doesn't hurt my feelings one bit. But these kind of problems will not require the tabular method. You won't need it. Because you look at this, and remember that x to the 10th. Oh, they're still there. X to the 10th e to the x deal. That was kind of nasty, wasn't it? So you think x10 ln of x would also be just as nasty. Wrong. It is not. It's always just two terms, no matter what that exponent is. So you don't need a tabular method. You don't have to go step by step by step by step. So yeah, it's so if this next example, x to the 200, oh, I don't want to put that in Maple. It takes about 30 pages to show the answer. But sometimes I'll do that in a live class just for grins. But yeah, but this would be a nightmare if you had to do this problem with either e, sine, or cosine. Even with a tabular method, you'd have to take 200 derivatives in a row. Holy cow. But no problem here. That x to the 200 does not make this problem any more complicated as if it was just x squared. So that's nice to know. You let u equal ln of x, so the derivative will be 1 over x dx. If dv then is x to the 200, antiderivative would be 1 over 201 times x to the 201. And then I rewrote, so now I'm applying the u, where it is up here somewhere, well, it's around there, the integration by parts formula. So that's uv right there. Here are these two. v du, these two. Now, once again, I wrote the x, 1 over x is x to the negative 1 to make this easy to combine. Makes that x to the 200. I wrote this as 1 over 201 squared. Okay, that's correct, but you may have to do it. But that's just, this 40401 is just 201 times 201. That's all. So real easy. So there's your answer. So that didn't, cause any more difficulty being x to the 200th power. All right, let's do some arcs here. Let's take a look at some arc stuff. For arc cos x dx. Now, I would leave the 4 with either u or dv. Take your pick. It doesn't make any difference. I would not pull the 4 outside the integral because then you would have to remember to distribute the 4 back. So I would leave it attached to something, and I just left it with the arc cos. So you see there's no x power other than d. There's no x power here. We'll do one with an x power in a minute. That's okay. Then that just means, but the u has to be the arc cosine part no matter what you do with the 4. That's all. The arc cosine is the important part. So in this case, dv would just be dx, but dv could be 4dx if you removed it here and moved it over here. But multiply those together, and they are in the right spot, obviously. So if you reverse them, even though they multiply together, at that very first example I've shown, you just haphazardly choose these, you're going to end up with a mess. Now for my formula sheet that we have for this class, I brought back the arc cosine, u dv. So antiderivative dv, of course, dx is just x. And then using the arc cosine formula, the derivative is going to be -4 square root of 1 minus x squared. And so here we go. So we have uv. We don't care what uv looks like other than we want it to be accurate. We're not integrating it. Perfect. Here's the part we're integrating. v du. Now I went ahead and brought this square root up. So you multiply these together, you have -4. So then that negative become positive. X, and then the 1 minus x squared to the -1/2. You got to be real careful here with this, because a common mistake, that radical form right there in the denominator, even though it's lifted up here, but it looks like it would fall under the arc sine category for integrals, but it is not. Similar looking, but the fact that we have this x right here means we're just going back to a basic Cal 1 substitution integral. So you got to watch for that. So yeah, I'll have students that just kind of give this problem on a test, and they'll have like this part arc cosine right, and then they'll have like arc sine written here, and that's not right. It's u sub, because that x comes right there and makes a substitution. All right, so basic substitution: 1 minus x squared, -2x dx, -1/2 du equals x dx. Perfect. And so here we go. There's the -1/2 from right here, the du. The 4 is the 4 right there. We have u to the -1/2 du. Okay, I didn't show the work for that, but it's real easy. The antiderivative of u to the -1/2 would be 2u to the 1/2. So we have the 1/2 and the 4 here make 2, and then we generate a new 2 from this antiderivative, so that makes that a 4. And then there we have our answer. 4x arc cosine of x minus 4, and then whether you write the radical or not doesn't matter. Of course, you're picking the answer. Just pick whichever form it's in. I wrote it like this. Maple put it back as a square root. That's fine. Same answer. And then plus c. So there we go. That was fun. All right, now we have, look at this one, x squared arc tan x dx. This follows the same process as the ln and arc, in the sense that you have to let u be the arc, and dv has to be the x squared. Oh, okay, I did something a little bit different here on this one, didn't I? Sort of, instead of drawing the connecting arrow, I must have decided halfway through there, forget that, I got tired of that arrow, so I just kind of color them to match. So put them together, there we go, there's your integral, beautiful, antiderivative of x squared, 1/3 x cubed, and the derivative of arc tan of x is 1 over 1 plus x squared. There's the arc tan formula right there. Now we put it in the parts formula. Kind of bring that up, make it a little bit bigger, I guess. All right. So let's see what we have. So we have uv, 1/3 x cubed arc tan of x. We don't have to integrate that, so that's terrific. Here's the part we have to integrate. Minus v du, and there's the v du right there. 1/3 x cubed over 1 plus x squared. Okay. Here's one of the rules for integration. You have an improper fraction. Obviously, we're not going to have this situation if there's a radical in the denominator, but arc tan does not generate a radical with its derivative. We have, whenever you have the power in the numerator is greater than or equal to the power in the denominator, you must use division to break this down into two separate fractions. You cannot integrate this otherwise. But it was, I don't want these to be too complicated division-wise. Well, let's go back over here. Now I put x cubed. The 1/3, I just left the 1/3 out. This time I left it outside. I didn't want to mess with it as far as the division goes. I left it out of the division step. You could include it if you wanted to. That's fine. But I just waited and distributed it right here. So I put x cubed, and I kind of lined up a couple of placeholders here, a 0x squared and a 0x. I always like to make sure I have something to line everything up under. So all you have to do is go how much, you're basically taking x cubed divided by x squared, which is x. So we take the x and distribute it through here. X times x squared is x cubed. X times 1 is x. Now remember, when you're doing division, you're subtracting. So obviously the most important thing here is that you're always getting rid of the largest term. The first term cancels. And this is an easy mistake to make people do when they're using division. It's tempting to put positive x right there where I have that green negative x, but you're subtracting. Like saying 0 minus 1 is negative 1. So that's why it's negative 1x. All right, since the power of x now is less than that divisor, that means your division is over. So that's it. As soon as this power of x is less than x squared, we're done. So you have to rewrite this as a fraction. So now I'm bringing the 1/3 back in. So there's the quotient x. So we're integrating x dx, and here's the remainder, x over x squared plus 1. So this is not integration by parts. This is just splitting this into two fractions. So it's x over x squared plus 1. All right, now, so you let u be 1 plus x squared, du is 2x dx, 1/2 du is x dx. Now let me explain something here. I didn't really write this out, but one thing, you see how this negative precedes this integral, so really this negative is kind of over here also. While I'm doing this lecture, I'll do this and then I'll get rid of it. That negative is going all the way through there. Now that'll work. So it makes this first one negative right here, but negative times that negative right there is what's making this positive right here. Ah, okay. So that probably would have been a common question, as people might go, oh, why is that positive? All right, so I didn't show that written form, but I just explained it. It's positive. And then because this integral just becomes, so we have the 1/3, obviously, for both of these. Antiderivative of x is 1/2 x squared. Du over u, that's good old natural log. So 1/2, 1/3, 1/6. You have 1/3. I guess maybe to save horizontal space on this, I just kind of changed it from arctan to tan inverse. That's fine. They're both correct. On handwritten exams or anything like that, I always tell students that, yeah, you can write it either way. I don't care. Both are acceptable. All right, so we have this part that was already here. And now we have minus 1/6 x squared plus 1/6 natural log of x squared plus 1 plus c. And it has the official UH seal of approval. There's the maple. Looks good. Looks terrific. Okay, here's one, just arctan by itself. This one actually will be a little easier. I probably should have, that didn't hurt anything, but I probably should have started with this one and then put that's all right. This one won't be division. So there's your u and your dv. U is arctan, dv is dx. Antiderivative of dx is x. Derivative of arctan will be the derivative of 3x, which is 3 over 1 plus 3x all squared. So it's not 3x squared here because you're squaring the 3 also, so it's 9x squared. So we have uv, x arctan 3x, and then we have v du, which is 3x over 1 plus 9x squared. When I did my substitution here, I just kind of chose to use a different letter. I mean, you don't have, as a student, you don't have to do that, but I did that just so it wouldn't be confused with if I used u again, just to not confuse it with that u. But obviously, you're free to use u again if you want to. So this is real easy. No division required, straight substitution. You end up with a natural log here. So this one's pretty good. Like I said, I probably should have put that one before the other one. And if you're feeling strong there and you want to try, this one will have division involved in it. Probably if I had to guess, it'll probably have two division steps up here instead of one. Might have to go another division around there. So that could be fun for practice. I'd recommend it. Now, integration by parts can also work for algebraic types of functions. Ironically, this doesn't have to be done by parts like the other ones. There's a technique that I showed in Cal 1 where this could be done without integration by parts, well, mainly because we hadn't learned it in Cal 1. So the thing, you bring this up, and when I'm first teaching integration in Cal 1, because you look at this and go, when they're first learning integration by substitution, you know, a student would be expecting that to be 3x squared, because that way the derivative would give you the x that you needed right here. But not the case here. So you still let u be 2 plus 3x, and then your du would be 3dx, and then 1/3 du is dx. So the million-dollar question is, how do I get that x? And you get that x then by solving u equals 2 plus 3x. Solve that equation for x. So if you just do it algebraically, move the 2 over, divide by 3, you have 1/3 u minus 2. That equals x. Perfect. So you put this in here. There's u minus 2, well, with the 1/3 on the outside, and the other 1/3 comes from that du. There's two separate 1/3. Both of them belong. U minus 2 is this x up here. U to the negative 1/2 is that radical brought up. And then you just distribute now. It's just in parentheses here is to the first power. You can distribute. So u to the negative 1/2 times u to the 1 is u to the 1/2. U to the negative 1/2 times 2 is 2 to the negative u to the negative 1/2. And you just do the power rule. So you have the first one will be 2/3 u to the 3/2. The second one will end up being 4u to the 1/2. So you end up with this answer. And because you have this 1/9 in front that you distribute through. So there we go. We have this answer. Now suppose we did this by parts. We'd want the u to be x, the dv be 2 plus 3x, the negative 1/2. I didn't show all the work here, but this would not be difficult. It would just, to integrate this part right here, it's just a straightforward substitution. Oh, actually, I did do it. Okay. I did show a little more of it than I thought I did. So you just get a little substitution going. So you have w to the negative 1/2, 1/3 from right there. Power rule. So you end up, the v ends up being here, 2/3, 2 plus 3x to the 1/2 right there. There's your v. So it's a just basic substitution integral to go from here to here. All right, so we have uv, which will be these two terms multiplied together, minus v du, which v, as you see, is the 2/3 right here, this part, times du, which is just dx. So actually, you're just integrating this thing one more time here with a 2/3 in front of it. So we already know this. Well, actually, I'm sorry, we're not integrating the same thing. My fault. That was a negative 1/2 exponent. The process is the same, but it's not the same term, because it's not the same thing, because it's negative 1/2, positive 1/2. But the substitution process is the same. You're going to generate another 1/3 right here when you take the substitution. So you have the 2/3 times 1/3, and then you integrate w to the 1/2, which will be 2/3 w to the 3/2. So you multiply all that together. 2/9 times 2/3, you're going to get 4/27. So you get this answer. Now, this is the answer I just got, and then I'm labeling for you here that I just drug down the answer that I got the other method. So on visual inspection here, it looks like I did something wrong. The good news is I did not do anything wrong. Those are actually mathematically equivalent, nor you would not be asked to show this, at least not by me, to show that they're equivalent. So instead of doing all the algebra to make them match, because one thing to keep in mind about integration, when you take the antiderivative, that means the derivative of the answer is supposed to be what you were integrating to begin with, right? So in other words, the antiderivative of 2x is x squared. because the derivative of x squared is 2x. So even though these look different algebraically, because they're much more complicated than that and can be rearranged to look like each other, all I need to check is that the derivatives match up. If the derivatives equal what we're integrating, then I know that they're both right. So you see, I took the top one and it maple and it got it real quickly. Now the second one, the one right down here, I had to sort of, it took the derivative correctly, but I had to give it one more, simplification process. But look at that. They're equivalent derivatives, and just, once again, it's very important to see that, okay, that was the actual function that I was differentiating. So that's not necessary for an exam, but it should show you, yeah, they're both right. That's all I'm trying to show. Okay, this is, I don't know if you have to really, if you just kind of learn what I taught you earlier, you'll be fine about when to choose u, what to let u be. This is a little acronym. I don't know, I call it liate. I don't know, whatever it is, but it's order of what you should choose for u when you have two things together. Ln, log, but actually some of these are kind of equal because you're not going to have ln and arctan in the same problem. So it's kind of irrelevant. You could switch these two and it wouldn't matter. You could call it ilate if you wanted to. But anyway, so that's the choice of u. Algebraic function would be the next choice. So you see what they're saying is you choose u to be like ln or arc before you do x, but you choose u to be x before trig or the e. That is exactly what I said earlier too. In other words, the algebraic part is the u whenever you have x's and cosines and e's and sines. We don't have to worry about tangent. But then it's dv. The other ones take priority on being u before x does if ln and arctan. So I don't know. If that helps you, by all means, feel free to use it, but it's not something you're required to memorize. Now this next problem, I'm going to let me zoom out on this for a minute. Sometimes I'll do this one in class, sometimes I won't. This will absolutely, positively not be on an exam. But I'll leave it there for a second if you want. Well, it'll be in my notes, but if someone happens to be just watching this video that's not taking a class from me, that's terrific. You can at least see this and take a picture of it if you want to, obviously, and look at it later. But yeah, I'll do that one in class. And sometimes if I feel like I'm running behind, I'll skip over it because I know I don't put it on a test. But I just want to mention one key step to this process down here, then I'll move on. It involves something strange that you normally wouldn't see in integration. Is that long story short, if you do an e and a cosine, actually it doesn't matter what you choose for u and dv. But what happens is if you don't reach this point right here, it would be an infinite loop process, and you keep going on and on and on. And let me just mention this one part here. You have to do integration by parts twice, because then what you do, and this seems kind of weird, but you look at this equation and you actually add an integral term from one side to the other. That seems kind of strange, but yeah. So like this one, think of e to the 4x cos of 2x dx all being like a term, like an algebraic term, like x. Well, you look at this, it has the same term, doesn't it? It just has a 1/4 right there. That's the only difference. That's just a numerical coefficient. So what you're basically doing is, it's like you're adding x plus 1/4 of x to make 5/4 of x. That's why there's a 4/5 there. So if you're interested in looking this over, just see that's, so it's weird. The only way you're going to get out of this loop here and finish this problem is, as soon as you do this, it cancels this integral by adding it to the other side, and now you have an integral only on the left side, and there's no integration left on the right side. So then you have it. Now, of course, what the step I didn't show is there would have been a 5/4, which means I multiply both sides by 4/5. So that's an interesting technique. This one I copied out of the book. I don't put this on a test either, but it's secant cubed, and it shows you what to choose for the u and the dv. But this is the same kind of idea, and I just kind of wrote this idea. And in other words, to solve this, you have to realize that you have to add a secant cube integral to both sides to be able to get it. So it's similar to that last one in that aspect. It's adding an integral, adding integrals as like terms. That kind of new and strange idea. You don't normally think of integrals being something you add together as algebraic terms, but you can. You just never needed to before. Yeah, so like this one, because actually, we know antiderivative secants on our formula sheet, ln of sec plus tan. So you add this one over there, and you see you end up with two secants there. And like I said, those are not questions I put on a test. But all right, so I believe that concludes this video on integration by parts.